In this video, we're going to look at indefinite integration, which is the reverse of differentiation. We will think about why there's a constant of integration in this procedure and what it means, and we'll look at a few examples. Integration can be thought of as the reverse of differentiation. It's the process by which we can determine a function when we know its derivative. Thus, for example, if we know that dy by dx equals g of x, then we can say that y is the integral of g with respect to x, which is written like this. For example, suppose we have dy by dx equals 6x squared minus 26x plus 20. Then y is the integral of 6x squared minus 26x plus 20 with respect to x. It is worth noting that these two expressions are just different ways of writing the same thing. They are equivalent. We can deal with this integral term by term. Well, we know that if we differentiate x cubed, we get 3x squared. Thus, 2x cubed differentiates to 6x squared. Turning to the second term, we know that differentiating x squared gives 2x. Thus, 13x squared differentiates to 26x. Finally, we know that differentiating a linear term gives a constant value. Thus, we have 20x. Putting these together, we have the result 2x cubed minus 13x squared plus 20x plus a constant. This result can be checked by differentiating y and comparing the result with the original function. Okay, but why have we added a constant? Well, let's look at what the function looks like if we don't add a constant. Just to check, we differentiate and we get 6x squared minus 26x plus 20, as expected. Now, as an example, let's look at the same function with a constant 2 added to it. We again get dy by dx equals 6x squared minus 26x plus 20. Similarly, if we subtract 2, we have this function, which again gives us the same derivative. Here we see two more functions either side of the original one, with 4 and minus 4 added as the constant. We usually write functions of this type using a letter to represent the constant, often using the letter c. We can see that all of these functions generate the same expression for the derivative. So what does this mean? Well, let's look at a point on the central curve, which corresponds to c equals 0, and look at the gradient at that point. If we take, for example, x equals 1.5, we have this point. Calculating dy by dx at this point, we find the curve has a gradient of minus 5.5. Now, if we look at the points on the other four curves for the same x value, we can see we get the same gradient because the curves have exactly the same shape. They are simply shifted in the y direction. The same is true for any value of x we choose. The expression we have for y, with the plus c term, thus describes a family of curves, all of which generate the same derivative. This family is infinite in size, as c can take any value, positive or negative. Here we see a general formula which holds for functions of the form ax to the power of n. Note, this formula doesn't hold for n equals minus 1, an exception we'll deal with later. Okay, so let's look at a couple more examples. Here we have the function 4 times x cubed minus 3x squared plus 5x minus 1. Now, because we need to deal with these term by term, I'm going to expand the function, multiplying throughout by 4. This gives 4x cubed minus 12x squared plus 20x minus 4. Now we can use the formula above to perform our integration. We have the integral of f with respect to x equals x to the power of 4 minus 4x cubed plus 10x squared minus 4x plus c. This second example appears to be of a different form on first inspection, but actually we can rewrite f as x to the power of minus 2. Integrating, we get 1 over minus 2 plus 1 times x to the minus 1 plus c. Tidying up this result, we have minus x to the power of minus 1 plus c. This can also be written as minus 1 over x plus c. Let's now look at some examples of other types of function. First, we have the function g of x equals x to the minus 1. This was the 1 power of x that the rule we have just been using does not apply to. Well, x to the minus 1 can be written as 1 over x. Here we use our knowledge of differentiation, since we know that differentiating the natural logarithm gives the function 1 over x. However, we have to think a little more here. If we look at the function y equals 1 over x, we can see that 1 over x is not defined at x equals 0. The curve tends to plus infinity for positive values of x close to 0, and tends to minus infinity for negative values of x close to 0. There's an infinite discontinuity. Further, we know that ln x is only defined for positive values of x. We thus need to consider what happens for negative x. Well, let's consider the function ln of minus x, which is defined for negative x. We can differentiate this using the chain rule. We have d by dx of ln minus x equals minus 1 times 1 over minus x. The minus signs cancel and we get 1 over x again. Thus, for positive x, the integral of 1 over x is ln x, and for negative x, the integral is ln of minus x. The integral is thus the natural logarithm of the modulus of x, which is valid for all x except x equals 0, when neither 1 over x nor ln x are defined. We also need to add our constant of integration c, of course, since we are performing indefinite integration. This next one is more straightforward, since we can effectively apply the chain rule backwards, yielding 1/3 times e to the 3x plus a constant. This next one again requires some more thought. However, it unravels fairly easily if we differentiate the function x times ln x. Applying the product rule, we have x times 1 over x plus 1 times ln x, which reduces to 1 plus ln x. The integral of ln x is thus x ln x minus x plus c. Now, what about this function? Here we use our knowledge of logarithms and rewrite the function as e to the x ln 5. This is of the same form as the second example above, e to the 3x, but with the constant ln 5 instead of 3. The result is thus 1 over ln 5 times e to the x ln 5 plus c. And converting back to a power of 5, this equals 1 over ln 5 times 5 to the power of x plus c. Finally, we look at the first three trigonometric functions. Integrating sine ax, we have minus 1 over a times cos ax plus a constant, which is again just using the chain rule backwards. Similarly, the integral of cos ax is 1 over a times sine ax plus a constant. And finally, the integral of tan ax is minus 1 over a times ln of mod cos ax plus a constant. For this one, you might want to try differentiating ln cos ax to satisfy yourself that this is true. We have looked here at indefinite integration, which we have seen generates an infinite family of solutions. Definite integration, in contrast, results in a single numerical value and can be used as a means of finding the area under a curve, amongst other things. This is dealt with in an accompanying video entitled Definite Integration, which also includes a brief look at how to use integration to calculate the average value of a function.